Hello, welcome. I'm Susan Nash, Aapg, and I'm delighted to introduce you to a wonderful wonderful webinar hosted by Aapg Deep Learning Technical Interest Group, and is presenting Unboxing the Black Box, New Techniques for Understanding Drivers of the Delaware Basin Performance by Camilo Rodriguez, IHS Markit. So I just wanted to give you a little bit of background about the series. The Technical Interest Group is a TIG, and it's one of Aapg's special interest groups that focuses on sharing information, opening opportunities, and also hosting workshops like this one. And you're really thrilled about it because what these are eminently practical, but they also give you a chance to meet each other and also talk about some of the new trends and tools and how they apply, not just for today's activities, but for future as well. So they give you the tools to succeed. So our speaker today is Camilo Rodriguez, and he is the lead of the Analytics and Data Science Group for Upstream at IHS Markit. He is responsible for research, development, and implementation of new technologies around business intelligence, data analytics, and machine learning in the IHS Markit software and content. He created Analytics Explorer, a data science platform to boost the efficiency of geoscientific workflows for the E&P industry. He has 18 years of experience. And anyway, it's just very impressive. And I would just encourage you to take a look at the Zoom profile as well to learn more about Camilo. We're really happy to have him here. I also would like to take a minute to introduce you to Patrick Ng, who's the director of our technical interest group, Deep Learning. So welcome, Patrick.
Oh, thank you, Susan. And for those who have not had the opportunity to participate in the Aapg Deep Learning Tech, I welcome you to join. Our focus is very simple. These are challenging times. What we hope to do is to, as a community, we connect the science, particularly geoscience, with AI machine learning to help us pivot so we can make better, more prudent decisions each step along the way and manage and thrive in energy transition. So for example, to the screen left of my ear, that's the Western waterway set in place 80 million years ago. And right here is roughly where Permian is. So today we're excited to have Camilo, who not only have vast experience in business intelligence and data analytics, but also he speaks geo. He's a geologist by training. So without further ado, welcome, Camilo.
Thank you so much, Patrick. Thank you, Susan. I want to start, well, first sharing my screen, obviously. If no, we don't go to any place in this meeting. Okay, who can I start here? Okay. Screen 2, sorry about this. All right. So everybody can see my screen right now, like an IHS Markit background?
Yes, we do.
Okay, perfect. Oh, sounds good. All right. So first of all, I want to say thank you to every one of you for taking the time, many of you during the lunchtime to listen my presentation and all the things that we are doing regarding machine learning in IHS Markit. Patrick and Susan, thank you for giving me the opportunity to be over here. Well, I also want to mention after the introduction that Susan and Patrick did about me, I also want to recognize the contributors of the work that IHS Markit in the upstream energy is doing regarding machine learning and data science. So thank you to Jijun, Mateus, Ivan, Cesar, Hamed, Hui, and Jeff for the contribution on every single of the methodologies that we are doing over here. Okay, with that, let's go ahead and get started. Let's go with the action. I want to start just with the questions. Do the geoscientists and engineers make $1 million decisions just because a computer says so? Are we going to trust a machine that we just put data in, give us an outcome, and blindly make the decision based on that? Well, this is a virtual event, but I kind of reading most of the minds right here, and more likely the answer for us geologists and reservoir engineers is no. We need to understand every single thing. Everything has to have relation with physics, with logic, right? So we don't gonna trust on that. But let me ask you a second question. When it's about fraud detection and protect your identity and your credit cards, why do you prefer? A, that your bank have an accurate fraud detection model? Or B, your bank have a model not as accurate, but that can be explained, okay? So in other words, do we want like a message in our cell phone, hey, somebody's trying to buy these expensive clothes in Paris. Is you yes or not? You know, easy, we hit no and end of the problem, thank you, fraud detection, we are safe, right? Or on the other hand, when we are checking our statements in the bank and we found some expenses that we didn't do, and we have to call to the bank, hey, to dispute those claims, right? We don't want to do that. And the bank say, oh yeah, I see those, but let me explain you the nice trends that we have saying like the robbery is being incremental in some specific cities. At that point, we don't care about that, right? More likely, in these terms, we need accuracy, right? Well, do we really need to choose? In theory, yes. The complex models in machine learning are very accurate, but are very hard to interpret. And the simple models are very easy to interpret, but the accuracy is highly sacrificed. We're going to talk a little bit about that. Simple model, what happened? Simple model, all of us are familiar with. Basically, is the linear models or nonlinear models. We have a bunch of features, attributes. We want to predict something based on those features. And basically what we do is to find a curve that fits every one of the features, right? And that we can explain, right? Even if it's linear, if it's non-linear, then we convert that non-linear relation to linear in order to have an equation. And once we have what we can explain in a linear way and with an equation, the input of every one of those features, right? So what every one of those features mean, we sum all of them and we provide an answer to the people. And they make a decision based on that answer. As I said before, pros, easy to understand. Who does not understand a linear model, right? Easy to explain, easy to comprehend, is amazing. We can find relations with physics. Is making sense the geology, is making sense the completion strategy, right? By the cons, accuracy is highly sacrificed and we are losing information. By only rely on just a simple trend, maybe your fraud detection could be one of those anomalies right here that we cannot explain, for example, okay? On the other hand, we have the complex models. Same deal. We put the features in, something happened inside that we don't know what is going on, and then we give the information to the humans so they can make decisions. Example of those black box model are obviously neural networks, very complex right here. You can see the bunch of lines, layers, you name it, right? Or tree-based algorithms. Over here, easily, in a good model, you can end up with more than 300 trees. How can we interpret that? It's very hard to do. But those models give us accuracy, give us reliability, and as you get more data, the better they get. Cons, who can explain this, right? No, I mean, nobody. Why we are making the decisions? Why we should drill a well right here, right? In the fraud detection, yes, sure, but drilling a well, why we are making tight decisions? Do you fail sometimes, model? When can I trust you the most, right? So those are the cons if we don't understand the inside of Black's model. So what we are proposing is, hey, let's unboxing this black box. Are there methodologies that allow us to look at inside that and get inside of everything that is happening? And what those methodologies can do, because those methodologies exist, is actually tracking down feature by features. And instead of creating an equation like in linear models, those methodologies tend to create a K-map with a contribution factor, if you wish. It's kind of the difference why this does. So if I can show you that, I want to get this across you, we can remove those cons, and actually we can add an additional pros. We can understand the contribution of every model input. We can back up any decision we do. We will know when to trust. And something that you will be surprised with the Delaware Basin example that we are showing here, we can see hidden patterns that we couldn't see before, right? So these things will allow us to do that. And we don't have to modify, manipulate data. That is the best thing about it. So let's go back to here. Do we really need to choose? So let's focus on the part of moving the accuracy to also being interpretable. This is what we are going to show. Okay, I'm not going to explain every one of those. I'm just going to mention this is some of the model explicability methodologies that is being used in modern machine learning in all the industries, okay? So in fact, some of the things that I'm taking to present today is taken from a conference from the medical industry, all right? So all of the industries are like us, right? So we need to understand, we need to know why. So this is some of the methodologies that can explain complex models. Partial dependent plots, which is this one, permutation feature importance, accumulated local effects, individual conditional expectation, and the one that we are going to focus the most today, this is the only one I'm going to explain, is the Shapley additive explanation chart. For now, it's just names, right? Who cares about the names? What I'm going to show you next is what we have done in IHS with some of those methodologies and what answers we could get in the Delaware Basin, and not only in the Delaware, but in some other basins as well. So how IHS has been using some of those right now and is exposing our products. Okay, the very first thing that we do is, okay, let's create a prediction model, a production prediction model of the Delaware Basin. One of the methodologies that we prefer to use because we have seen is more accurate for this specific problem is XGB, XGBoost. No any machine learning methodology is beating XGBoost for this type of problem, predicting production. It's the most accurate one. So, okay, we are using one of those tree-based machine learning to come up with the model. And here is the first thing. Permutation feature importance. One of the methodologies that I showed in the previous slide. What is Titan doing for us specifically? Well, permutation feature importance is telling us, hey, in the Wolfram Delaware Basin, what is driving your production mainly is the feature horizontal length. The horizontal length that you are drilling right here is the main driver. Second driver is the structural, the geological location, the depth of the formation of the Wolfram A in this case. Gas-oil ratio is extremely important. The amount of fluid and proppant, thickness of the formation. Notice that over here, TOC is also showing up as the most important one. So this is what permutation feature importance can do for us, showing how important is every feature, all right? If it's positive, if it's impacting positive or negative, we don't know. Permutation feature importance doesn't stop right there, but we can find the answer later, okay? So there are other methodologies that can tell us how important it is. So this is why this analysis does. And basically, in few words, is how the accuracy of the model is going to be affected if one of those features are removed. So it's kind of the principle behind permutation feature importance. Once we have permutation feature importance, it also can add more transparency in the error metrics that we are doing in our models, right? For example, what we are seeing over here is that in the y-axis, we are seeing a measure of error. So we see that as we include more features in this order of importance, as we include those features in our model, the error is starting to go down, go down, go down until it's flattened, right? When it flattens means, hey, these other attributes right here is not hurting or improving your model. So it's kind of okay attributes, you know, the important drivers of the production in the Wolfram A is the one that I just mentioned. In other words, the location of the structure and how we are completing the well. So this is one of the ways how we are using one of the attributes. Okay, the second thing, all right, we have the model. We know why the attributes are important. Now, how can we translate this geologically? Well, the model was built using well data, and we test the model obviously with well data. Now that we have an acceptable model, what we are going to do is to fit the model that was already created with geological grids. So imagine that every cell of my geological grids that have petrophysical properties, imagine if like any of those cells is a new well, for example, right? So we feed all of those cells into the tree model to try to predict production. And the result is this map right here, a sweet spot map of production that is telling us, hey, if you drill a well in this area, you should expect around 400,000 barrels in the first year of production. If you drill a well in this area, you should expect 300,000 barrels the first year of production. This is what is telling us. Hot colors, sweet spot area, cold colors is not as good geological area. But guess what? Over here, as we as a geologist expect, we let the geology flow. We are not constraining the geology. The geology is what it is. But in our model, we are using completion parameters. Those are the ones that we need to normalize. We let the geology flow, but how can we normalize the completion parameters? Well, right here is where we can use another interpretability technique of the ones that I mentioned over there, called accumulated local effect. What it does basically is finding specifically how every one of those features is impacting the production. For instance, right here, this is telling me that this is an example with horizontal length. As we increase the horizontal length, we have a general trend that the production increases. Notice that if we analyze the trend of this plot, at some point we also see a flattening in around 9,000 feet. So this map says, hey, you will produce 400,000 barrels in this spot, assuming that your wells, you are drilling a 9,000 well. What if I don't want a 9,000 feet well, or if I don't have the acreage to do that, or I have to reduce it? Well, the sweet spot is not going to change. What is going to change is maybe the predicted barrels, right? So maybe if you go to 7,000, maybe it's not going to be 400, but maybe 350, right? So this is the point. So this is how we can use accumulated local effect. This one is another example with the spacing. So this is telling me as we space more and more the wells, is working better for the production. And at some point, the behavior is flat. And like that, we can interpret some other engineering variables to come up with maybe something that we can consider optimum completion parameters. This is another way that we have used that. But now, let me step to the second part of the presentation, and it's the one that we are going to focus more today. Now we are adding a new one, Shapley additive explanation, and we are calling factor contribution analysis, and you will see it what. Let me start with an analogy over here. So here is Mr. Rodriguez going to the bank and asking for a loan. The bank analyzes my information and says, hey, Mr. Rodriguez, sorry, your loan is denied. As a customer, I want to know why, right? Why my loan was denied. And I go to the bank and I complain to the manager, and also the manager, they need to have some answers, right? So this is how Shapley works. Imagine that the bank has an acceptance rate of 20%, right? So if they predict that a user, right, has a higher risk of no pay of 20%, the loan is denied. Okay, so this is what they put as a base. Okay, obviously, if I'm between the 19% or down, there is nothing to explain, right? But if my predicted risk was 55%, then what the bank should explain to the user is what is special between our base and your score, your risk, 55%. This is the piece that we need to explain the user, okay? And then they come and say, hey, you are very young, so it's a high risk right here, and that risk is adding 15%. But you also are an instructor of extreme sports. It's a very high risk profession. That one will add 40%. And you know what? We check and you already have one loan with another bank. It's adding another 15%. But in your favor, you have very good capital gains last year. So because you have very good capital gains, boom, it helped you 35%. So at the end, the sum and subtraction of those different scenarios is the one that came with this number, okay? And this is exactly what a Shapley analysis can do. Instead of creating an equation, it tracks down feature by feature, obviously with complex mathematical equations, to get with a factor contribution of every one of the components. So how can we relate this to oil and gas? Okay, so here we have what I just showed you. Let me swap this out. Okay, in oil and gas, our base will be whatever we are predicting of production. Okay, what is the average, either first year or 2 years or 6 months or 5 years, production of every well in the Delaware Basin? That one will be our base. In this case, for the Permian Basin that I'm doing here, the Delaware, we are working, predicting the first year of production. So if you have a well that produces the average in the Delaware Basin, there is nothing special about that well. It's the average, right? But if you have an overperforming well, now I need to know what is special, right? I need to know why this well is way above the average. Or if I have an underperforming well, we need to know also what is special in our case, why the well is not behaving how we should. We don't want wells producing less than the average, right? So this is what it is. Now, the other thing that we are going to replace, in my analogy, there were personal features. age and profession is kind of personal feature, right? The age was young, so it added 15% to the risk. The profession was a high risky profession, it added 40%. So both of them contributed 55%. And now the financial features, because all those features can be grouped, then the number of loans didn't help, it increases 15%, but the capital gains helped me, so it goes down for a total of minus 20, right? So you can group this stuff. How can we group or do the analogy with the production? Well, let's replace the personal feature by acreage quality features. Here in the acreage quality feature is where the geology is included, right? So location is included in there, things related to geology. And let's change the financial feature by the things that we can control in the oil industry. We can control everything related to engineering, completion, and spacing features. So we can group every one of those. So this is how this is playing a role over here. Okay, so then what is special now that we have like a big picture understanding of what Shapley additive explanation will do, how this can be applied specifically to our cases. Well, for example, it works if you have a bunch of data, if you have geological data, TOCs, porosity, permeability, it's great, we need to take it, right? But what if sometimes that geological information is limited? Especially with public data, why the companies report the most and are obligated to report its production and engineering, right? But not much geological data, okay? So how, if we have areas where technically we don't have access to a bunch of geological data, why this methodology can help us? Can we estimate good acreage like that? And also, if we can combine it, we can create models using information from other basins. Can our model get better and better, more accurate with the time? Anyway, so this is what we are going to do. So let's start with the demonstration in the Delaware Basin. What matters? So if I go to IHS Markit, our database, and I take all the wells that are producing in the Wolfgang Basin, specifically in the Delaware, and I plot the first year of production, is what you can see in the y-axis, the first year of production of every well against the lateral length of every well, this is what we get. We don't see any relation here. We see that, hey, we have wells with 10,000 lateral length that are producing awful, but I also have 10,000 that are producing, I mean, my best well is right there. And like that, I have all the spectrum in 7,000, very bad wells, good wells, right? So there is not a clear relation. Well, kind of 0.3 correlation coefficient, but there is not something concrete right here. And this is what the data is telling us, okay? The reason, obviously, we know is because this is a multivariate problem. Maybe this well with 10,000 feet is in a bad acreage location, and this one is in a good acreage location, and that makes the whole difference. If we take a look to other parameters like well spacing, I mean, we know, I mean, we learned that from practice, from the university, everything. I mean, the less the wells are competing from the same resource, the better the production should be. Why we are not seeing that here? Why in well spacing, we actually are seeing a 0.013 correlation coefficient down. Amount of propant. In theory, the more propant you inject, the fracture keep open and it should be better, right? 0.1 correlation coefficient, right? We don't see, this is what the data is telling us. Well, the Shapley methodology can transform these plots in something like the one here. Now, this is one of the benefits. Now we can see, hey, all of my wells, every one of those points is one of the users asking for the loan, right? In the same way that they could respond me why my loan was denied, They can respond the same for the 1 million, 2 million people going and asking for why my loan was approved or denied, right? So every one of those points is a well. With my analogy, is one person, right? So every one of those is analyzing this factor contribution. And when you plot now the real lateral length, the real variable lateral length against the factor contribution of every one of those properties, you are getting those visuals, those plots that makes sense. This is why the geology is telling me, hey, in the Permian, in the Delaware, look at that. In around 1,200 feet is where we see a general flattening. 1,200 should be acceptable well spacing for the Delaware Basin, right? Here is clearly showing, yeah, the more lateral length, the better production, what have you. How this plot has been generated. Let me go to the next slide and start showing that. As I told you before, the very first step is to generate a predicted model using a complex and accurate machine learning algorithm, in this case, extreme gradient boosting tree. Our model for the Delaware Basin we consider is very good. Delaware is complicated compared with other basins. Let me tell you that in other basins, we have errors of 10%, 14%, you know, but errors below 20% for data science is acceptable. So in the Delaware Basin, our error is 19%. This error is calculated with testing data only, not training data, all right? So we have a good error. Now, if we plot what our prediction model is giving us, right, against the actual production, actual in the y-axis, in the x-axis versus predicted in the y-axis, we can see we have a good model with a R-squared of 0.88. Here on purpose, I put two additional lines. This one right here in the horizontal axis is the average value that our model is predicting for all of the wells. So the average value in the first year of production is 143,710. And the real value, the real average with real data in the first year is 143,760. So notice that the average prediction is very good, right? From this point moving forward, we are going to work with this value, the predicted average value, to explain why some wells are above average and why some wells are below average. So let me now minimize this and let's go back to our analogy of the loan. I'm going to choose randomly one person, in this case, one well. Why this well down here is below the average? Here is the answer. Hey, the contribution of the lateral length is hurting in 47,000 barrels. So notice, it's quantifying in the same units of what we are predicting, all right? In the same way that our analogy, the age was hurting 15%, here is in terms of the barrels, is hurting 47,000 barrels. The completion was not good, right? The amount of proppant is hurting 39,000 barrels, what have you. The location is hurting 12,000 barrels. So we can see exactly every one of the components and say why this well was bad. Conversely, I want to randomly select one of the wells that are very good right here and see why. Hey, this well is in a good geological location. Look, 48,000 barrels is due to this in a good acreage. Notice that 34,000 barrels is related to what I'm calling here TVD. This TVD is basically the landing zone, okay? So related to the structure, right? So it's geology, in other words, right? And also was completed properly. Anyway, so like that, I can see like any person that apply for a loan. Now we can explain what's denied or not. Right here, I can see every single one of the wells and give an answer. All right. So how these plots are then being generated. The one with this nice trend and things like that. So let's pick the well that I have currently selected, and let's focus on the contribution of lateral length. For this well that I have currently selected, it's telling me that its contribution for lateral length is 72,000 barrels. So basically right here, we are plotting the contribution for that well, 72, versus the real lateral length, all right? So if I select other well, then the contribution right here is -10. So as you can see, -10 versus its real lateral length, and so forth. If I just start selecting more and more and more, this is how this plot is being created for every one of the attributes, all right? But look at something. Remember in the introduction, I was saying that this type of methodologies, they show more data, right? So instead of showing only one general trend, let's analyze by operator. What is the trend that Oxy has? What is the trend that Concho has? What is the trend that Noble Energy has, right? So is everybody being benefit in production per lateral length equally? Or there are some companies doing better than others per lateral length, for example? So look at the level of granularity that we can go with having something like that. So let's, for example, put the case of Cimarex right here. Let me put column, just picking two random right here. So notice that clearly we can see that drilling wells of 10,000 lateral length, for whatever reason, right, Cimarex is being good, being productive in this domain, at least in that area. Anyway, so this is the type of analysis that we can do. Let me go to the next one. Well, this is, we're gonna go faster over this. This is the results of every one of the attributes or features that we are using. So for the geologists right here, this one is the gas-oil ratio. Notice that this is also making sense, right? As we get more gas in the mix, obviously it affects the production of oil, right? So this is what we want to see, is going into the right direction through vertical depth, right? So the deeper we are in the structure, it seems better. Anyway, so this is the things that we can analyze. Okay, now let me go back one more time to the analogy. Remember, when we were asking the loans, we could do two things. We could separate personal features versus financial features. We group those features, right? Well, let's try to do the same here. What about if we just combine everything related to the things we can control, which is completion and spacing and things like that, as a one feature, and the things that we cannot control, like geology, location, is what it is, right? So let's do that. So let me just one more time pick one well right here. And this well is telling me, hey, again, the contribution of everyone. But what if now we sum well spacing plus fluid per propan ratio plus propan per foot plus footage lateral length, and we call it this completion. And things that we cannot control, like the location of the well, the depth and gas-oil ratio, let's call it location or contribution of geology. So this is exactly what we are doing right here. So basically now we trim this down to understand a little bit better, and we combine everything in contribution of location, contribution of completion. So now we can see better that this well here that I select randomly is good, mainly because the completion, even though geology is helping, but this is mainly because the completion. One bad let me just choose one bad well. Look, randomly I'm selecting one very bad well, is hurting the location. Okay, so basically this is what we can do. So if we can group this as we are doing into items, if you wish, then let me show you another plot right here. This plot, let's focus on this one right here in your lower right. So what we are doing is I'm plotting in the x-axis the contribution of the location, and in the y-axis the contribution of the completion. Remember, 0 is average, okay? 0 is not necessarily is bad. 0 is average. Everything close to 0, there is nothing special about it. It's average, right? So here I color by quadrants. So in this quadrant right here are the wells that are in a favorable geological location and also have been completed properly. So let me just select this quadrant, and then we can see, hey, EOG is the main player in this quadrant. Okay, it's being highly benefit from this type of location. Here are the wells. Let's see who is doing good in areas that maybe the geology is not as good as that one, but are doing good completion practices to keep up with the production. So we can see Oxy, Parsley, Diamondback are over here, okay? Anyway, so this type of analysis is what we could do. But let me, again, as a geologist, I would like a little bit more. Can potentially we convert this type of analysis right here just to analyze geology and maybe compare with other geological maps or sweet spot to see what the results are? So let's try to do it, okay? So now, okay, well, before that, yeah. So one of the things, I'm sorry about that. So before doing that, before trying to create a better map, notice that in this slide, I want to show you another extra analysis. So again, back to our 4 colors, we can see how with the years, all the companies are moving into the blue, yellow. So the completion practices are increasing over the year. This is expected, right? This is what this is showing us. Over here, we can also see how we are starting to move for maybe it's unfair to set bad completion practices, because maybe in 2009, we were completing the wells with the best technology available. But maybe 2009 compared with 2020, of course, is a huge difference, right? So that's why 2013 maybe was considered bad practices compared with today. But we can see the trend, right? As we move, as we advance into the years, we are seeing more wells that being drilled in those quadrants. So this is another way to understand and validate our models. I notice also this is showing us with the colors. And again, because we do the granularity, this level of granularity, we can also see this trend by company, as you can see, all right? So I can analyze every single company and see how they are doing. Look at, for example, Exxon, how is, anyway. You can see this with your eyes. So now let's go back to, can I create a sweet spot map out of these, right? So this is our next thing. So right here, one more time, we have this, but this time randomly, we separate the location, the geology, the contribution of location by different colors. Being blue, the wells that are being benefit mainly because of location. So that has to be related to excellent geological area. Green, wells with good geological areas, they are being benefit for geology location. Yellow is not bad, yellow is average geological location, right? So this is the area. Poor and bad, geological conditions, okay? So over here, we can see that obviously the majority of the companies, operators are yellows, which is good. One more time, clearly, we can see EOG, many of the wells are being benefit for this section right here. And anyway, so here is how it looks in a map. If we grid this, let me just put the map of contribution of geology. This is what we are seeing right here. Notice, obviously, colors matching in this way. Let me remove the wells for a moment so you guys can see kind of an acreage quality map that we are creating with that. If we compare, so Jeff Bowman, so he's a very good geologist right now helping us. He's validating every one of those maps with real geology and seeing if it's making sense, and we are finding very good results with this methodology. Anyway, so again, we also, when we have geological information available, we put it in there. When there is permeabilities, porosities, TOC, as we also did in the Delaware. But this methodology can be amazing when that information is missing, and more amazing if you also have the information. But anyway, so we can see right here the good acreage areas for the Delaware Basin in the Eddy counties, Lea, Lowen County. Let me just focus a little bit in this part right here in the sweet spot area. And you know what else we did over there? We ran an analysis. If you will remember, with our transformation plots, with the Shapley plots, we saw that in around 1,200 feet of well spacing is kind of an optimum stuff, right? So I want to be 1,200 feet far away from wells that had been already drilled in that area in the Wolfram. So let me just put that distance right here. Let me subtract this 1,200 feet, and over here is resulting of just the remaining areas that potentially the companies can go and drill. Let me just, for the fun of this presentation, let me just plot the wells so you can see the areas that have been already drained already. Okay, this is the analysis of geology. In 3 more minutes, very quickly, I'm gonna go to analyze now the completion, and then we finalize this. So now let's forget about geology. Let's take a look to the completions. What this methodology can do for an operator, right? So here, one more time, we have all the players in the Delaware Basin, and this time the colors, they don't correspond to geology anymore. Now they correspond to good completion practices and bad completion practices, okay? So if we analyze, for instance, let's pick the first one, Oxy, right? So we can see things like, hey, in the years, so what Oxy is doing in terms of completion, so we can see an increase of percentage in that. We can also see what treatment companies Oxy or any other company here is using. They obviously are using more pump costs, followed by a Schlumberger and things like that. But if they want maybe to analyze, if I put this in proportions, so we can see, hey, who is proportionally drilling better wells for them, right? So what have done is Schlumberger maybe for Oxy during the years, right? So this type of analysis can be done. Let's do a quick operator analysis now, all right? So just to finalize this, this is an operator analysis. So let me select EOG that now we know is being benefit for good geological location. So I'm selecting EOG, and we can see here in our top chart the production of EOG over the years, okay? So this is production, cumulated production. This one is how much this production has been benefit because the location. So notice that our zero line, which is again the average, the majority is telling us, hey, it's benefit for the location. In completions, EOG is very, very close to the average line. Well, they don't need to suffer much about completion because the geology is helping them, right? But let's take a look to, let's compare this with Parsley, for instance, one of the companies that show up like a good, doing good completions, right? So this is Parsley production, similar with the years. Obviously the geology right here is showing Parsley is not in a as good area as the EOG does, but they are catching up with some completion stuff right here. Anyway, so this is things that we can do, benchmark companies. This is the level of detail that we can have with this. Because of the time, I mean, I just getting into the end. So this is pretty much the summary. So we have seen that with this methodology, there are still a lot of opportunity in the Delaware Basin. Our inside group is doing more detailed analysis. We are just the data science group right here. So, but there are other analysis with more detail about that. But there is still a lot of opportunity in the Permian Basin, Lee, Loving, Erie, and Winkler County, benefit for good geological positions. Ward, Reeves, and Culberson counties, even though they don't have a good geological, as good as the other counties, we have seen that the production can be similar with good completion practices. Obviously, because the geology in the long term, it will decline faster and they were gonna have more gas and things like that, but this is what we are seeing. These methodologies are showing us, are proving like how the completion techniques have been improving with years, you know, and the most important thing, there is no need to choose anymore between accuracy versus interpretability. We in IHS already have implemented interpretability tools with powerful machine learning model to give more insight to our customers with our data, right? Not only raw data, but now what else we can do. And as you could see in our focus with the factor contribution analysis, we can go as granular as we want in terms of benchmarking per year, per operator, well, etc., etc. Finally, just want to say thank you everybody for listening to me. Hope you could bear with me, and I hope I could be clear and I don't confuse you. And if anybody is interested in see the results of our machine learning analysis like this one that we did for the Delaware, we have it for almost any basin in the United States. Please contact me and we are glad to take you over this. Susan, I go back to you. Thank you.
Okay, thank you. Wow, that was wonderful. And I have to say that your selection of kind of an illuminating analogy really, really makes a big difference. I just really like it. And I want to make a quick announcement before we take a few questions. First of all, thank you to IHS Markit, our sponsor. IHS Markit is also sponsoring AAPG Academy, which is launching on July 14th, which will be John Holbrook talking about geothermal for now and the future. But I just want you to stay tuned. IHS Markit is sponsoring all 5, and we'll have CEU opportunities also. Okay, so here are some of the questions. So first of all, Misong Young says, is this analysis done by Spotfire?
Spotfire was used only for visualization of the results. So all the methodologies that we are using happen behind the scene of Spotfire. Is not in Spotfire. So we have our proprietary Python code with our machine learning methodologies that we modify. So all of those happen behind the scenes, and then we just plot the results in the Spotfire. So it's only using as a vehicle to visualize the results. And yep, so the code is our code, and we have it also embedded in one tool we have that is called Analytics Explorer that works with the Spotfire.
Okay, that's great. Okay, Carlos Molinari says, an astonishing presentation, very impressive. Thanks to Camilo for sharing. Well spacing was presented as an important completion issue, and my mouse is not cooperating. So did you see the question? Can you read the rest of it? I can't seem to scroll down. Well spacing, do you see it?
Well spacing was presented as important issue. And so how would the child parent well, like those well interference temporarily is normalized or included in the model? That's the question from Carlos Molinari.
Perfect, thank you, Patrick.
Carlos, that is a very good question. In fact, we are actually working on that. So we are considering two things right here in the model. One is well spacing as it is today, right? And the other is well spaced by vintage. Okay. So in the model, we can see that obviously it creates an impact. In the model we included by vintage. So what was the well spacing when you drill the well? If you are using a 2017 or something like that, what was the well spacing at that time? By the new wells of 2019, obviously they will have more competing wells, right? So yeah, so we have the well spacing analysis done by how it is today in the picture today, and also by vintage. And we currently are doing a more detailed research on completion strategy. What is the ideal number of wells that can affect the net present value of the reservoirs? That is another project that is ongoing with IHS. And yeah, we are working all over well spacing right now.
Great. Clinton Tippett has another question. Wells are often choked back during initial production by and for a range of reasons. How does this affect your analysis, given that oil is your main performance criteria?
Clinton, thank you so much for that question. We have the question before. It's a really good point for all of our clients. You are completely right in terms that when you compare the production with few months, right? So the choke is a factor, right? But as you build the model 1 year, 2 year, 3 year, 5 year, that choke is not a factor anymore. It's not important anymore. Okay, so that is what we have seen. Now, with that said, the first year of production that I presented here today is a very good representation of later months, short-term months, and long months as well. So choke factor, in other words, is important in the first life of the wells, but we have seen that after 1 year, year and a half, whatever, that effect is being minimized for the prediction model.
Great. Okay, so thank you this is from Jose Omojola. Thank you for the great presentation. I have a couple of questions. Maybe we just have time for one. Have the first year prediction results been compared to reservoir history matching results?
Yes. In fact, this is how we compare the accuracy of the model. Okay. So when our predicted model is actually compared with the history of the well, this is where the 19% of error that I was telling you is coming from. All right, is by comparing with real data. Yeah, so that is obviously the first thing that we do is critical. Your second question, when the data is being used, is it an average value of the feature that is used? For example, completion data are the number of perforation length, depths, etc. used. Or is an average value used in the training model? No. We actually use the real value per well when we train the models. When we train the models, we use the data as is, the value that corresponds to every single well. The only part when we normalize is when we show a sweet spot map, okay? When we present the sweet spot map, that when we let the geology flow, right there is where we said, hey, this is the sweet spot map if you have these completion parameters. But to create the model in the first place, we use real data, real value, no normalization, no anything like that.
That's super interesting because it kind of leads to a debate between supervised and unsupervised models. So anyway, okay, so we have time for one more. Awesome analysis in X versus Y dimension. What might it look like in the third dimension of the reservoir?
That is a good point. And actually, recently, one of our users actually in Chesapeake, he was starting to get into more dimensions with this. He was trying to use with our partial dependent flow, the accumulated local effect plot that is only 2 dimensions. He tried to add, which is completely valid, it's a methodology over there, as a color in the background, another dimension. And the result was amazing. So basically, it shows compatibility. I show it over there with Chesapeake. We have to implement it somehow. When he showed me that, I mean, the user over there, we immediately started, looking, researching, and it's something that we have to do. Let me tell you, the results looks good. When you put a heat map underneath of these 2D plots, the other attribute highlights as well, and it's good. The results are good. Unfortunately, I didn't do it here, but it's something that for sure we have to look at.
Okay, so I'd like to we have one more. Oh, I guess we have no more time. Well, I'd like to give Patrick a few minutes to say a few words, and then we'll say thank you to everyone and thank IHS Markit and you specifically, Camilo, for a wonderful presentation.
Well, Camilo, I want to congratulate you because you speak geo. So one of the things with data science conference that you always go to, at the end, they show a confusion matrix. And I'm more confused than any, but today there's no confusion matrix. And so thank you, and we enjoyed thoroughly.
Thank you, Patrick. Thank you for the feedback. Thank you, Susan.
Thank you. Well, thank you, everyone. And you'll be receiving an email that has a link to the recording and also a link so you can sign up for Aapg Academy, which will be free, but you can also sign up for $35 to get more content and also CEU. So wonderful on every regard, every level. So thanks again and have a wonderful day.